Welcome everybody, and thanks for coming to this new appointment for theory lectures for and by young researcher. Today and tomorrow we have here Angelo Ricciardone from the University of Padova. Angelo is a great expert in gravitational waves prediction and detection, with a particular focus on the early universe. In these two lectures, he will talk about primordial gravitational waves and interferometers. Before proceeding, remember that this is a very formal meeting, so please don't be shy. Feel free to unmute your microphone and ask questions. Angelo, when you want.
Okay, great. So can you hear me? Can you see me? Can you see the paper here?
Yeah.
Okay, great. Let me first of all thank you for the opportunity to give this lecture at this very interesting this very interesting initiative that you did. I think that it's very useful that young researchers meet, interact with each other, and exchange idea and how to say eventually start project for future collaboration. So I would be very happy to be in Florence today, but let's say I hope that there will be the possibility in the coming year. Okay. So sometimes I'm sorry for this, but sometimes my camera freeze. So and you see me frozen, and so if it is happens, so or I switch off, or please tell me, and I will fix it. So let me okay, let me drink a bit of water, and then we start. This is the bottle of the University of Padova. I will not move so much. I don't want that Padova lose students and money. So let's see if this up. Okay. What I will tell you today and tomorrow is something about gravitational waves, in particular stochastic background of gravitational waves and interferometers. As Rocco say, I will mainly focus on primordial gravitational waves. There is not so much time, so I will on some stuff I will be a bit quick, and I will try to tell you that future gravitational waves detector, in particular interferometers like LISA or Einstein Telescope, will be able to extract physics and information about early universe models at small scales. Okay. So, and then I will firstly introduce gravitational waves in a basics way, because I didn't know the exact let's say curriculum CV of all of you, and then I will introduce the let's say the basics observable quantity that usually are used when we play with gravitational waves and the interferometers. Okay, so since these are lectures, feel free to interrupt me whenever you want with all the questions that you have. No matter if they are stupid, simple, because it's a pleasure to answer. And I will give you also during the lecture, I will give you also some references, let's say key references that usually we use whenever we don't remember how to do something. Okay, that it happens every day. Okay, let's start. So tell me if you read well, because I don't write very well. And now it's time to start. Okay, let me give you the outline of these 4 hours that we will spend together. Okay, so I will first of all introduce introduction about gravitational waves. So I will tell you how gravitational waves emerge in GR and how we play with them in cosmology. Then I will quickly go through the frequency band and let's say how the different frequency bands are related to the different sources of gravitational waves and the detectors that we have that we have and we will have in the future for detecting gravitational waves. Then I will move to gravitational waves and interferometers. As I was saying before, I will teach you, I will tell you what are the observable quantity that we usually see in the plot and how we can understand them and how they derive. And finally, I will focus on the main topic of these two lectures, the stochastic background of gravitational waves. Okay. Gravitational waves, and I will characterize them. I will explain you characterization. I will explain you later what characterizing mean. Observable quantity. Sources of stochastic background, because probably you already know that we have two main sources, an astrophysical stochastic background and the cosmological stochastic background. That they will again be composed of many sources that I will tell you during the lecture. Okay, so if you have any question and you are too shy, so feel free to send me an email even later, angelo.ricciardone@pd.infn.it. So don't be, please feel free to write me with any question or comment that you have. Okay, so let's now give you. So I don't know if it's too fast or too slow. Please tell me. Let me give you now some references. Okay, let me give you some useful references that can be useful during these two lectures and can be useful also for you in the future. For sure, the Michele Maggiore's book. Michele Maggiore's book is the first is Gravitational Waves, volume 1, that is theory and experiment. Okay, let me write everything, otherwise Michele will complain. Oxford University Press. Okay, first book. Second book, Michele Maggiore, Gravitational Waves, volume 2 is Astrophysics and Cosmology, Oxford, again, University Press, 2018. Okay, this is 2018. The first one is 2007. Okay, so then there is a good review by Caprini and Figueroa, Danny Figueroa, that is only focused on cosmological background of gravitational waves. This is, let me give you the archive number. It's archive. It's 1801-04268. Then there is, this only describes cosmological background of gravitational waves. Then there is another review by people in Padova, not me, Gravitational Waves from Inflation. It mainly focuses on inflation by Guzzetti, Bartolo, Liguori, and Matarrese, and the archive number is 1605.01615. Okay, so then one of my first paper within the LISA collaboration that I coordinated and I contributed, that is, this will be mainly useful tomorrow, where we list, let's say, we analyze where we analyze some inflationary models that can be probed with the LISA detector, and the title is Science with the Space Based Interferometers method. LISA is probing inflation with gravitational waves, and the archive number is 1610.06481. Then there is another recent paper that we did, is on the reconstruction of stochastic background with LISA. I will give you, because in this I will give you these references, even if I will not let's say tell anything about this, because in these references we essentially we do all the things from the basics. Okay, so, and then it's useful if anyone wants to have a complete overview of all the quantity that we will discuss during these 4 hours. Reconstructing the spectral shape of a stochastic gravitational wave background with LISA. Okay, and the archive number is 1906.09244. Okay, and then there is a final one that is another review, mostly focused on interferometers and all the sources, a review by Joe Romano and Neil Cornish, that is very useful, because there are a lot of information about the theory, but there is a lot of information also about the detectors, and also about the statistics that is beyond the gravitational wave searches. For stochastic gravitational wave background, a unified treatment. Okay, and the archive number is 1608.06889. Okay, so these are the main references that we will use this during the 4 hours together. Okay, so any question? No. Okay, so then let's start. Okay, let's start with let's start with a bit of history. Okay, of gravitational waves, that is can be useful to remember the main step of the gravitational waves history. Okay, 1916. Okay, Einstein predicts the existence of gravitational waves. So I didn't specify the acronym. As you can imagine, when I write GW is gravitational waves. When I write SGBW is stochastic background of gravitational waves. Later on, I will give you all the details about this. As a solution of the GR equation. Okay. And so even if people think that we arrive at 2015 to have the first detection of gravitational waves by the LIGO-Virgo collaboration, we have already another indirect measure in 1964 of gravitational waves, observing the pulsar PSR 1913 plus 16 by Ulls and Taylor. Okay, the first Ulls and Taylor. This was the first indirect measurement of the existence of gravitational waves. Later, I will show you the plot that for the first time confirmed the existence of the gravitational waves. Then we arrive at a few years ago, where Weiss, Barish, and Kip Thorne won the Nobel Prize. Okay. For the contribution to the gravitational waves measurement. Okay. So let's say that these are the four main steps in the gravitational waves history in this 100 year. Okay, so essentially 100 years ago, Einstein predicted the existence of gravitational waves. After 100 year, we had let's say the first direct detection. Let me add here direct detection by the LIGO-Virgo collaboration. Okay, so let me now give you some general fact that start to introduce you to gravitational waves. Okay, so essentially, as I told you before, gravitational waves emerge naturally in GR. They are essentially so it's a bit wired to write everything, but propagating oscillations of the gravitational field as light, essentially at the same way as light is a propagating oscillation of the electromagnetic field. Okay. So essentially, this is the comparison that we can do between gravitational waves and light and electromagnetic waves. So just to give you an idea, so the frequency of the electromagnetic waves goes from 10 to the 4 hertz, where we have the radio waves, to 10 to the 20 hertz. Okay, so 16 order of magnitude. And here we have the gamma rays, for instance. Okay, while on the other hand, the frequency of gravitational waves, as far as we know, they go from 10 to the minus 16 hertz the cosmic microwave background up to, let's say, I stop here at let's say 10 to the 4 Hertz, even if, as you probably know, there are sources of gravitational waves that peak at much higher frequency in the megahertz or in the gigahertz. But here is the let's say the range of most plausible sources, and these 10 to the 4 Hertz correspond to the usual let's say frequency from compact binary system as neutron stars merging. Okay, so and here, as you can see, we have 20 orders of magnitude. Okay, so what is the general statement, the general problem of the gravitational waves? The gravitational waves, the gravitational interaction is weak. Okay, sorry, is weak, and what is the problem of this weakness of the gravitational interaction? That for these reasons, gravitational waves are difficult to detect. Okay, so this is the reason why we didn't detect yet gravitational waves with the CMB yet. We didn't detect, let's say, I would say we didn't detect primordial gravitational waves with the CMB. We didn't detect primordial gravitational waves with interferometers. We detected gravitational waves from binary black holes because you need very large masses moving at high velocity in order to generate a gravitational wave signal detectable with an interferometers. Okay. So as you can understand, we cannot generate gravitational waves on the Earth. We don't have this kind of masses, so we need astrophysical object. Okay, and this is in an easy way astrophysical object that generate a signal with the high amplitude. Okay, so I already told you about the Alsen-Taylor gravitational waves indirect detection. Let me just show you this plot that you have probably seen. So as you can see here, there are the experimental data which perfectly overlap with the GR prediction. Okay, so as you can see here, GR already predict that when these two pulsars inspires among each others, they lose some gravitational waves, let's say power, that is precisely predicted by GR. And as you can see, this is a really amazing prediction of the existence of gravitational waves. Okay, this is on the y-axis there is the shift of the perihelium of this system, and on the x-axis there is this variation along 15 years. Okay, and you see a perfect agreement between the prediction of GR due to the energy loss in gravitational waves and the experimental data. So this is a very amazing, was the first amazing results considering gravitational waves. Okay, so after the, as I told you, after the first indirect proof of the existence of gravitational waves in 2015, precisely the 14th of September of 2015, we have the first direct measurement of gravitational waves from a binary black hole system, okay, where the two masses, where M1 was around 36 solar masses, M2 was around 29 solar masses, okay, at the redshift of 0.09, okay, and you can understand why you need this astrophysical object to generate gravitational waves. So let me show here. Sorry if I go. We are in a, let's say, we are in the first 15 minutes. So it is a bit of history and general information. So here is a partial list of all the gravitational waves detection that we have up to now. So as you probably know, we finished in October 2019 the third run of the LIGO detectors. And up to now we have 50 events. Okay, we have 50 events in the O1, O2, the sum of O1, O2, and O3A runs. Okay, this is the O3 runs is not finished. And among these, so I highlighted one of these. Do you, someone of you has in mind why I highlighted this GW170817? So let me do also some question to see if you're still there. Chat.
There's an answer in the chat.
Okay, wonderful. Anyone has a another answer? Yes. Okay. So as Morteza say, so this was 170817 was the first detection of a binary neutron star system. And as you know, this had a lot of implication for cosmology because we had strong constraint on the late universe, in particular on GR. Many models of the late universe were ruled out or partially ruled out. As you probably know, it opened the era of multi-messenger astronomy. And I would also say that this is something on which we are working on. It opened also the way on multi-messenger cosmology. Okay, so this was one of the most important detection of gravitational waves. And let me also say that up to now we have two detection by a system of two neutron stars. Then there is one that is not clear if it's a neutron star plus a black holes. So we are at the stage where essentially we have a kind of a detection per week. Okay, this is more or less the period of the gravitational waves detection by the LIGO collaboration. Okay, so let me go now more a bit of general in details to general information. Okay, as I told you at the beginning, in the outline of the talk of the lecture. So the next step, this is the introduction. Okay, the next step is the frequency band versus sources versus detectors. Okay, so let me now give you an overview of which are the main frequency band where we expect some signal, some source to emit, and also the detectors that works in this frequency band. Okay, frequency band. And sources. Okay, what I usually think that is the first frequency band is the high frequency band, HF, where frequency between 10 to the 4 Hertz to 1 Hertz. Okay, this is the let's say main known frequency band where you know this. Later I will tell you which are the detectors that works in this frequency band. Then we have the low frequency band, LF, where we have frequency between 1 Hertz and 10 to the minus 4 Hertz. And this is the frequency band where space-based detectors will work. Then we have the very low frequency band, low frequency, very low frequency band, LF. And here we are between 10 to minus 7, 10 to minus 9 Hertz. And here is something, a frequency band where experiments like nanograv, PTA, IPTA, and so on are active. And you probably know that we have some recent claim of a possible detection of a stochastic signal. And then we have the extremely low frequency band, extremely low frequency band, that is between 10 to minus 15 and 10 to minus 18 Hertz, okay? And this is where CMB experiment works, okay? Like Planck did, and in the next years also other experiments like Lightbird will try to detect primordial gravitational waves. Okay, let me go through these. So for some of you, so up to now is too slow, too fast, is it okay? Too simple?
It's okay, it's okay.
So if we want to complicate the life, we can, if you want. High frequency band, okay? So it's the domain of the Earth-based detector. So here, Earth-based detectors that are mainly interferometers or resonant mass antennas, okay, that are not very used anymore because they have not enough sensitivity to detect gravitational waves. So what we have here, okay, we have LIGO, as you know. There are two detectors, Mford and Livingstone. Livingstone. They are 4-kilometer arms, and they are separated by 3,000 kilometers between them. So then we have close to you, we have Virgo in Pisa. So it's a 3-kilometer arm. So these are 3-kilometer arms. These are both two L-shape interferometers. Okay. Then we have another German detector that is in Hanover, 600, that has not enough resolution because it's just 600 sensitivity because it's just 600 meters. Then we will have the future, okay? We will have third generation interferometers that are very promising. So among these, we have Einstein Telescope, that will be, there is the possibility that will be built in Sardinia. There is a competition between Sardinia and Netherlands, and Cosmic Explorer in US. This should substitute the two LIGO ones. So just to give you more information, it's not clear the final configuration of ET, most probably it will be a triangular detector composed by three essentially detectors in this configuration here, okay, with each arm of 10 kilometers, okay, and this is 60 degree. So Einstein Telescope will really open to us, thanks to its sensitivity, a window both on let's say early universe models and also to a lot of sources, astrophysical sources, and we'll have as a guaranteed let's say target the stochastic gravitational wave background for sure of astrophysical object, of astrophysical origin. Okay, so this is the story of the high frequency band. Let's see the sources in the high frequency band. Sources in high frequency band. Okay, what are the sources here? So they are stellar collapse to a neutron star or black hole that gives a supernova. It is the rotation and vibration of a neutron stars, so pulsar in principle. So the main known source is the coalescence of neutron stars and stellar mass black hole. With a range of masses that is below, let's say, 10 to the 3 solar masses. So later we will understand why. And then we have, let's say, we are, I would say, in the limit for reading mechanism. Some mechanism particularly tuned that could peak in the very high part of the spectrum. Okay, so let's now move to the low frequency part. Okay, low frequency band. Sorry, the low frequency band that is between 10 to minus 4 hertz and 1 hertz is the frequency band of space-based detector, as I was saying before, and in particular of LISA, laser interferometer space antenna, and other detector like this IGO, BBO, probably you know some of them, and in the recent years they join other Chinese detectors like Taiji, Tian Queen, that is probably written Tian Queen. I'm not sure if this is the right way to write it, but what I will focus more in this lecture is about LISA. Okay, LISA is a giant interferometer, triangular again, in the space this time. Okay, where each of the arm is 2.5 billion kilometers. Okay, this is the and this again, okay, I don't enter in the details, but is again composed of 3 different detectors. 2 of them are completely independent. The third one is used for the noise calibration. Okay, so it will fly in the optimistically in the 2033. It will have a life mission of 10 years, a science mission of 6 years. What I can tell you more, okay, it will fly in an heliocentric orbit following, trailing the Earth. And what I can tell you more. So, okay, an important stuff is that why to go in the, so in order to reach this range of frequency is necessary to go in the space, because, you know, below, for F minor that, let's say that than 1 Hertz, you are limited by seismic noise, okay, on the Earth. So the only way to explore this range of frequency is to go in the space. So let's now see the sources in this frequency band, okay? In the low frequency band. So the life here is quite rich. We have white dwarfs that will play the role as a foreground, essentially, for LISA. Then we have neutron stars, binary neutron stars. Then we have small, let's say, solar masses, black hole, small black hole in spiraling let's say of masses with masses from 3·10⁵ to 3·10⁷ solar masses. Then we have in spiral and coalescence of stellar mass black hole binaries with masses between, let's say, from 100 to 10⁷ solar masses. And then, of course, we have the stochastic background of gravitational waves, let's say both astro and hopefully Cosmo. We will see that here. Let me go more in detail later, or tomorrow probably we will see some of these. In the cosmological sources that LISA, among the cosmological sources that LISA can see, there are, of course, let me call them inflationary model. We have to go beyond, for all these detectors, both on the ground and the space, we have to go beyond the slow roll models of inflation, so inflationary models. Then we have phase transition. Tomorrow I will tell you more about the energy at which and the kind of phase transition that need in order to have a signal let's say in this frequency band. Then we have cosmic strings. And then we have some things that became very popular, second order gravitational waves induced by scalar perturbation. That generate essentially what you probably know that are primordial black holes. Okay, black holes. So essentially, primordial black holes, they are nothing more than second-order gravitational waves induced by large scalar perturbation. Okay, so okay, so let's go now to the third frequency band, that is very low frequency band. Okay, this is for frequency between 10⁻⁷ Hertz to 10⁻⁹ Hertz. Okay, let me tell you something here. So So this is was a bit, let's say, unexplored up to a few years ago. But then last year, as you probably know, there was this claim by the Nanograv collaboration of a possible detection, let me stress possible, of a signal of stochastic origin. Okay, so so the physics behind this frequency band is a bit different, or better. The kind of detection, the instrument, let's say, to detect these gravitational waves in this frequency band is a bit different than the one used by interferometers like LIGO, Virgo, LISA, and the other that I mentioned. So I will not go in details to this. Just I will mention that in this kind of range, the detectors are usually pulsar timing array that essentially are they measure the time shift in the time of arrival of the pulsar. So this is pulsar timing array. What I will tell you more is that it's very important to say that it's not easy to find, let's say, the origin of the signal because for a compact body, compact astrophysical object to radiate in the very low frequency band, it must have a mass larger than 10 to the 11 solar masses. Okay, so and these are supermassive black holes. Okay, supermassive black holes, and so astronomers suggest that there are no black holes with such masses. So then there is the trouble if the signal, the claim that they did last year is of astro origin, or is something, let's say, for me at least, more appealing, that could be a signal of coming from cosmic strings, because they can emit in this frequency band, or something related that are phase transition. Okay, and there is a lot of activity on this. I'm also giving some thesis and some papers, some project on this. Okay, so let me cover the last frequency band, extremely low frequency. Can you read it? Yes. Band, that is the one that covers the range 10 to the minus 15, 10 to the minus 18 Hertz. And it is related to really cosmological sources. And in particular to primordial gravitational waves. Okay, so in particular the gravitational waves that are let's say that are expected in this frequency band are the one coming from inflation, and we will explain now in the part more, let's say, we start with a bit more of physics models that how we can predict, let's say, the amplitude of this gravitational signal in this frequency band. Okay, and just to write here we in this frequency band we expect okay, we know that the experiment like Planck worked up to 5-6 years ago. Then we will have LightBird in the next year, and then we will have experiment like Stage 4, and or Core, the other experiment, or Pixie, and we will have a lot of still searches for primordial gravitational waves. Okay, so let me just show you. You can tell me why you didn't show us before, because I think that is nice to list step by step the list of sources expecting this frequency band, and also the kind of detector. So I hope that I convince you that we have a lot of gravitational wave sources. Having a lot of gravitational wave sources means having a lot of gravitational waves. We need a lot of gravitational waves detectors, because the range of frequencies is quite large. Okay, just to a summary of what I wrote up to now is this. Okay, so in the range of the high frequency band, we have mainly ground-based detectors, ground-based interferometers. And as I told you, these are LIGO, Virgo. Probably, sorry, I forgot to mention CAGRA also, that is active from 1 year. Okay, and LIGO India will be active in the next years. And here the sources are these neutron stars. Okay, and let me just for the moment focus on the x-axis. Okay, because I didn't tell you what is this H, and this is one of the target of the second part of the lecture. Because we don't know, at least yet, what this number means. In the low frequency band, as I told you, going below 1 Hertz, we need to move in the space. And here we have, as I told you, LISA, TIG, this IGO, BBO, and so on. And the sources are these ones: stellar mass compact binaries and massive black holes mergers. Okay, and there are also other sources. Of course, these are listed the most important one. Then moving lower in frequency, as I told you, we have pulsar timing array experiment. And here the main sources are supermassive black hole and cosmic strings. And moving further, here we have primordial gravitational waves and
sorry, Angelo, there is a question.
Yes. So your question is, are primordial gravitational waves different sources from inflation? Can you separate them to each other? So, okay, probably I was not so clear on this. So when I talk about primordial, can you read it? Okay. Primordial automatically means, let me clarify this. Okay, I will tell you also later, it means stochastic. Okay. When I talk about primordial, I mean, I mainly refer to cosmological sources, okay? So among these, probably we can mention the most important one, inflation. Phase preheating, let me say also this, or even if they pick preheating, if they pick at a different frequency, phase transition. Let me write here, because you know cosmic strings, for people that are expert, they require a cosmic. They require results of also a phase transition. Okay, at least some kind of defects. Okay, so these are the main let's say also from inflation I can write PBH. Okay, someone is not convinced about this, but for me it's like this. Okay, so these are the main cosmological sources. Okay, your question is totally right, in the sense that how we can distinguish them. This is written in the paper that I mentioned, reconstructing the spectral shape with LISA, because there are different ways to characterize. This was one of the point of the lectures of tomorrow. Of characterize and distinguish, separate the different sources. Okay, the first one is the frequency profile, and probably also the most useful and important. Frequency profile in the sense that okay, I have to anticipate something, but when we write the energy density, the spectral energy density of gravitational waves as an amplitude, let's say at a particular scale times the frequency, we need this, let's say, is a template for a power law signal. Okay, and these are some things that is mainly expected from let's say from inflationary models. Okay, there are thousands of models, but let's say what we expected is a amplitude of the spectrum, is a shape of the spectrum like this. While on the other hand, for instance, phase transition, as you probably know, are expected to have a different shape. Tomorrow I will show you some plot where we can see this. On top of these, cosmic strings again are expected to have a different frequency shape. Okay, and also preheating mechanism, and also this PBH, they have let's say different frequency profile. So the way to separate them, we hope, is to use their if we measure, is to use their frequency profile to characterize and distinguish them. On top of this, of course, let me also add, whenever we will measure a stochastic background, we will measure the composition, the combination of the astrophysical and the cosmological one. Okay, so one of the main problems which we are working is how to disentangle the cosmological from the astrophysical. Again, tomorrow I will tell you some particular value of this A and this alpha for astrophysical background and for cosmological background. But again, the frequency profile is another way to distinguish the different backgrounds and the different sources within the background. Okay, then we can use other let's say other tool. For instance, one on which we are working a lot is Ardhan Isotropids. Okay, so it's a bit technical. This, if I have time, I will tell you something tomorrow. But essentially, since gravitational waves travel along our universe, they meet, let's say, the large scale structures, and these induce both some anisotropies during the propagation and anisotropies during the production. So if you look model by model, let's say, or sources by sources, you can see that these anisotropies can be another way to distinguish the different mechanisms. Another way is non-Gaussianities. Okay, so Rocco is an expert of these and can also comment on this. But we expect non-Gaussianity mainly in cosmological sources of gravitational waves, not in the astrophysical background, and then other specific, more specific, let's say more specific features, that is like parity violation, because this would be an indication of a cosmological background, for instance, because we don't know up to now sources, astrophysical sources that can generate parity violating gravitational waves. Okay, these are the main tool to distinguish the sources. Is it clear? Okay, so let me conclude this part of the lecture saying that at very low frequency, so this is the range for primordial, mainly for primordial gravitational waves from inflationary sources. And again, I didn't enter into the detail because I want to focus on interferometers in this lecture. But here, let me say that the way to measure the gravitational waves, it is through their effect on the polarization of the CMB, and in particular on the B mode of the CMB. Okay, this is I will tell you something more in the second part of the lecture. So if it's fine, I would stop 5 minutes or 3 minutes just to, and then we'll pass to the second part. Or you want to continue? For me, it's the same.
I think that we can have 5 minutes break.
Okay.
Angelo,
Yes.
when you want.
Yeah. So, do you see the document camera or not? I should share again the document camera, or can you see it? Because I don't see anymore.
Let's see.
Okay, now probably I have to share again.
Okay, okay.
Share again, share again.
Okay, wonderful. So, let me. Let's restart. Of course, I'm late. Do you have any question on the first part of the lecture? It was quite an introduction. So it's any question, comment? No? Everything clear? Okay. Let's now move to the second part. Let me think a bit. Okay, because I was thinking that we need a bit of time. Probably I can skip some details, but let's move to the second part and be a bit more quantitative, because up to now we have been quite qualitative. Okay, so as I told you before, when I showed the last plot, you cannot know, or some of you don't know what quantity like HC, the characteristic strain, is, or omega GW, that is the spectral energy density, or the sensitivity, for instance, SF is. Okay. So the target of the second part of the lecture is to arrive from basics, from really the basic information of cosmology, to define this quantity that we usually use when we play with interferometers. Okay. So since the target of the lecture was primordial gravitational waves, I will start discussing from what I know a bit better than other stuff, that is inflation. Okay, so all of you knows that one of the best, let's say, one of the best property of the inflationary period, that is beside solving the shortcoming of the hot Big Bang model, like the horizon problem, the flatness problem, the entropy problem. So the most important thing is it is responsible for the generation of primordial perturbation. Okay, so I don't know if how many of you are familiar with the cosmological perturbation theory. Let me just give you the most important information. When we talk about primordial perturbation, I refer to scalar perturbation. So without entering into the details, these are the one that are responsible for the cosmic microwave background anisotropies, which are the seeds of the large scale structure that we see in our universe. Okay. So, and for many years, cosmological experiment has incredibly improved, let's say, the amount of information extracted from the observation of this scalar perturbation. On the other hand, as you can imagine, there has been always a lot of attention, but from the direct measurement by the LIGO-Virgo collaboration, the attention towards tensor perturbation, that are gravitational waves, is increased a lot. Okay. Again, as I told you, the main probe, I wanted you take home this message, especially for primordial gravitational waves. The main probe is the CMB. Instead, we are pushing a lot in this last year to show that also interferometers can give us information on tensor perturbation on the early universe. Okay, so then the main target of the lecture of this second part is to connect inflationary, let me call inflationary observable like the power spectrum I will tell you later what is a power spectrum, to interferometers observable quantity that are the one that I showed before: HC, omega F, omega GWF, SF. Okay, because this is something that I always it's never written specifically somewhere, so I think that is a nice stuff to explore in a lecture. Okay, so now let's give the basic for do this. Okay, so I told you about perturbation. Okay, what they means. Okay, if we write our LIGO element as you know in GR, the x mu, the x nu. So the idea of the cosmological perturbation is simple. You take your metric and you write it as a background quantity that depends only on time plus a small perturbation, a small fluctuation, okay? That depends both on space and on time. So this means that your line element becomes like let's say G mu nu, the x mu, the x nu. It becomes something like G mu nu of t plus delta G mu nu of x and t. Okay, the x mu, the x nu. So the most general we can show that the most general first order perturbation to a spatially flat, let me write one times for Friedman Lemaitre. I was muted.
Sorry, my error.
Ah, okay. Sorry. Walker, Friedman, Lemaitre, Robertson, Walker metric universe that, as we know, describe very well our universe is the following. Okay. So this is the most general line element at first order, -1 plus 2 phi. Later I will explain you what are these symbols that I'm introducing to A of t, bi dxi dt plus a square t 1 minus 2 psi dij plus 2e ij, okay, dxi dxj, okay. So let me tell you what these guys are, okay. So we have, first of all, we have phi, psi. Okay, let me first of all exploit what are essentially all the components. Bi is our vector perturbation that we can write as, you know, as a longitudinal and transverse component. Then we have the tensor part of the metric that we can explicitate, and we can write dije plus 2, partial di f j symmetrized plus hij, okay. These are written explicitly. So we have scalar perturbation, that are phi, psi, b, and e. Okay, so these, and these. Okay, these are scalar perturbation. Then we have vector perturbation that we usually don't consider in cosmology, because if you compute their equation of motion, you see that they are diluted very fast. Okay, and here we have Si and Fi, that they are proportional like 1 over A, where A is the scale factor that describes the evolution of our universe. Scale factor. Okay, and then we will have what is most important for us? Okay, what is the most important for us? These Hij that are tensor perturbation, that are gravitational waves. Okay, this is the object of the next 3 hours together. So since we are interested just in tensor perturbation, so let's write our metrics putting all the other stuff to 0. Okay, so it's much cleaner. Okay, so we have dt square plus at a square t times delta ij plus hij dxi dxj. Okay, so this is a of t is the scale factor. T is the physical time. So, and everything is ready. Many times in cosmology we also use the conformal time, that is related to the physical times by d tau equal dt over at. It's just a rescaling over the scale factor, and we can write. It's common to write also the metric in conformal time, because it's easier sometimes to solve the equation of motion, plus delta ij plus hij dxi dxj. Okay, so tau equal conformal time, xi are comoving spatial coordinates. Hij, that is our target, is a gauge invariant tensor metric perturbation. Okay. So so I don't describe all the steps to arrive, and all the let's say properties to arrive at a final definition of what this Hij is, but as you have probably seen in GR course, this is this Hij is the properties that is symmetric. That means that Hij is equal to Hji, is traceless, because we have to arrive at this definition here, we have imposed the traceless transverse traceless gauge. That means Hii is equal to 0, and this transverse. Okay, these are the properties of this guy here. Okay, transverse means that the partial derivative of Hij is equal to 0. Okay, so you could tell me that how much are the physical degrees of freedom. You could ask me how much are the physical degrees of freedom of this guy here. Okay, so if we start from let's say this is 3 by 3 metric. Okay, and we include and we consider the all the conditions that we imposed, we can see that starting from 9 elements, we have -3 that are given by the symmetry, -3 that are given by the transverse condition, -1 that is given from the traceless condition. This means that they are 2 physical degrees of freedom. Okay, what are these 2 degrees of freedom? They are the plus polarization that we usually heard, and the cross polarization of the gravitational waves. Okay, so we have an object that has inside 2 physical degrees of freedom, that are the plus and cross polarization. So this means that in a simple way, we can write this object like H plus A plus Ij plus H cross E cross Ij. So okay, so this is a way to write our physical object, because including what are the E plus and E cross are the polarization tensor. Okay, so we describe, we write our tensor perturbation using the polarization tensor. So, and these have useful properties that I need to list you, that will be useful when we will compute the power spectrum. Okay. So if P is our polarization, so then plus and cross, let me, as you know, write in this way. So we know that Aijp of K is equal to Aj of P of K. Okay, this is the symmetric properties transferred to the polarization tensor. Then we have the transverse properties that is translated on the polarization tensor in this way. K that is equal to 0. Then we have II of K P that is equal to 0. Then we have another properties that comes from the fact that our tensor is a real guy. That means that A to the minus inverse momentum is A to the Ij P star of K. This is complex conjugate. Okay, this comes from the fact that Hij is a real guy. Then we have another properties that comes from when we sum over the indices, Eij of P of K times Eij of K of Q, so equal to 2 delta PQ. These are completeness and orthonormal relation. Let me put here. And another one that is useful that you never find anywhere, especially when you have to write it in Mathematica, you never know how to do, and this instead of summing over the indices, you sum over the polarization, okay? And is LM of P, and this comes always into play when you have to play with second order gravitational waves. This is PIL PJM plus PIM PJL minus PIJ PLM, where this projection operator is Pij is equal to delta Ij minus Ki Kj. Okay, so here they are the properties. Okay, so as I told you before, since they are Hij, you have probably seen. Okay, this is much. Is a bit more technical, but Hij is gauge invariant. Okay, if you apply, if you make a gauge transformation to Hij, you see that is the only object that at first order is gauge invariant. Okay, this means that automatically means that this is a physical degrees of freedom. Okay, so when you go at second order, you have to be a bit careful with the gauge invariance, but still in some regime during the universe evolution is this guy is gauge invariant. Okay, so how we can arrive at defining the power spectrum from the beginning? Okay, so let me do usually when I have more hours, I do a detailed derivation of the power spectrum. Today, since we have just a few hours, I will do a fast derivation of the gravitational waves power spectrum. Okay, so I'm sorry for this fast, but 4 hours they are not enough. So the starting point is the Einstein-Hilbert action. So the Einstein-Hilbert action describes our let's say from the Einstein-Hilbert action we can derive our equation of motion and the solution that describe the evolution of the primordial gravitational waves. Okay, so what are these symbols here? Okay, small mpl is the reduced Planck mass. G is the determinant of the metric. And R is the Ricci scalar. So, so if you take this equation here, this action here, and you do the expansion that I did before, you plug in the metric that I show you before at second order. This is something that usually I can do, but now I have to skip at second order in perturbation. In a, let me write quasi de Sitter space-time. So the action becomes 2 means second order. The action becomes the following: m Planck square over 8 d tau d3x a squared, the scale factor, times g bar mu nu. This means that this is a background quantity, d mu hij, d nu hij. So very, very simple. Okay, so it's really, this is a first order quantity and this is a first order quantity. So this means that we have a second order first time first we have a second order action. Okay, so the easiest way to proceed is to decompose hij in Fourier space, because it's easier to manage. hij in Fourier space, so I usually use this convention here. So I write hij like a sum over plus and cross of HIJP times, sorry, of A sorry, this is A, IJP times H of P, okay, of X and tau, where this HP of X and tau is this is the convention that I use for the Fourier transform, a to the minus ak is kx times hp of k and tau. Okay, so this is our tensor perturbation in Fourier space. Okay, so if you take this guy and you plug in this equation here, you get this second order action. Okay, it's very easy. I recommend to do it as an exercise if you want. So what you get is d tau d3k over 2 pi cube a square of tau times, let me write here, h prime p of tau and k square minus k square h okay, sorry, this is omega square minus omega square of h p of k tau, okay? And this is our second order action in Fourier space, okay? And this is omega square. I will tell you soon. This omega square is essentially the dispersion relation, that is k square minus a prime over a, where prime means a derivative over d tau versus the conformal time. What is usually done, we use the canonically normalized variable p of p of tau and k, that is equal to mass Planck over 2 a of tau hp of tau and k. So, and if you do this exercise, you see that your action becomes the following, okay? It's canonically normalized plus cross integral d tau d3k over 2 pi cube times, let me write here, v prime, prime is always a derivative with respect to the conformal time, k and tau, square minus k of tau vp tau and k. Okay, so this is a simple equation essentially, right? So this is a Lagrangian of an harmonic oscillator, so that we are all familiar with. So the only difference is that in this omega here, we have this piece here that is time-dependent quantity that essentially include the evolution of our universe. Okay, so this action here is nothing more than so it is for a tensor. Okay, so I told you that is for tensor perturbation, but it's nothing more than an action of two real scalar field. Okay, so you can think as your action as for the tensor as the action for two real scalar field that are v plus and v cross with a time-dependent dispersion relation. So if you think in this way, so the easiest thing that we learn when we play with the harmonic oscillator is to promote them, these two fields, at the level of quantum field. So what you do is the same story that we learn. So d3k over 2 pi cube b of k of tau of ap, introducing our annihilation so this is a star, a plus p of k, sorry, a to the ak dot x. Okay, so what I've done, I promoted my field to quantum field, introducing a and a dagger that are my annihilation and creation operator. So if I plug, if I start from the second order action that I show you before here, this one. So the exercise to do is to derive the equation of motion. So because we need to know the evolution of these gravitational waves. If you do this, guys, and you compute the equation of motion, so we will get something like this. Okay. Okay, tau okay, equal to 0. Okay. What is this? So it is a wave equation. Okay. So this is a wave equation where the dispersion relation tau w of k is equal to k squared minus a double derivative over a. So we have discovered that our gravitational waves, this is the reason why they're called gravitational waves, it's described by a wave equation. Okay, so what are the, let me understand better how we can go towards the derivation of the power spectrum. So I wouldn't go too much into the detail. So if you okay, so let me give you just the easy way to find the solution of this wave equation. Okay, so the qualitative way, the qualitative solution of our primordial gravitational waves are the following. So what we usually do, we plug us into regime. The first regime is a regime where k squared is much bigger than a over a double dot over a. Okay, this is the regime called sub-horizon regime. Okay, so this means when gravitational waves are still within the horizon. Okay, so in this case, since a double dot, we can show that since the double dot, a double dot over a is something like, goes like a prime over double prime goes like a prime over a square. This means that k square is much bigger than a double prime over a, which means that k is square is much bigger than h squared. That this is the Hubble in co-moving coordinates. That means that k is much bigger than a over h. Okay, this is our horizon. This means that our modes are sub-horizon. In this case, the solution in sub-horizon regime if you neglect this term in the equation of motion, is very simple. It's something like VOK equal to A to the AK tau. Okay. So this is a very simple solution. If we go back to the to the original variables, that is Hij, that we defined before as going like A times A. Sorry, we define Hij over H as V over A. This means that our solution Hij goes like 1 over A. So essentially, it gets diluted by the universe expansion. So on the other hand, in the second regime, sorry, I was not so clear on this. On the other hand, when k square is much smaller than A double prime over A, so there are two possible solutions. So in this case, you neglect the k square in the equation of motion. You have a solution that goes like as the scale factor, and another solution that goes like V of k of tau, that goes like 1 over A square. Okay, so if you translate this in terms of H, this corresponds to a constant solution, and a solution that decays like 1 over A cube. Usually we neglect this because, of course, it's very diluted, and we learn that on super horizon scale, that means k much smaller than AH, the gravitational wave solution is constant. Okay, this is a very qualitative behavior of the gravitational waves. So we know that on subhorizon scales it gets diluted like 1 over A, while on it is constant freeze on super horizon scale. So so I didn't explain what is the horizon, of course. So I hope that many of you knows. Mainly, so if you don't know it, tomorrow I can say something something more on this. So I have other 10 minutes, right? So, okay. Okay, so if okay, so if we compute, so what I did was a really rough estimation of of the solution of the gravitational waves in the different regime. Okay, so so if we would like to be more quantitative, so I should go through the exact derivation. Okay, so I will not do it on the other hand. So I will give you the solution on the exact solution in the two regime. So then you will try, if you want, you will try to derive this equation, and if you the solution, and if you don't succeed, we can have another chat eventually in another time to show you how to obtain the solution. But you can also find on the reference that I give it to you. Okay, so just more quantitative. So a bit more quantitative. Okay, so so in the subhorizon regime, so the solution for the equation for the primordial gravitational waves is the one that that I show, and this is this is simple to solve. And as I show you, this is quite precise. Okay, the solution that I show is this one. This agrees with the one that I showed you before, this one here, except for this constant factor before. How do you fix this? So you fix this imposing that the vacuum of your theory. Okay, what we usually do, we fix it in a Bunch-Davis vacuum. Okay, so and this is you assume that your primordial gravitational waves as this in the vacuum as this Bunch-Davis vacuum, okay, as initial condition. So and this allows you to fix this normalization constant here. On super horizon, the situation is a bit more, so then this means that on super horizon we were almost precise. On super horizon, so on super horizon, the situation is a bit more delicate, okay? So super horizon means that the wavelength of your mode, the wave number, is much smaller than the Hubble radius. So if you, you know, A prime over A is our comoving Hubble rate. So if you do the double derivatives with respect to the conformal time, you get something like H prime plus H squared. So that if I defined the Slorol factor is 1 minus H prime over H squared, this is a Slorol parameter. So this is equal to something like 2 minus epsilon H squared, that goes like 1 over tau squared, 2 plus 3 epsilon, okay? Trust me on this. So if you plug back this guy in the equation of motion, you see that the equation of motion becomes the following: V double prime of k plus k squared minus 1 over tau squared nu squared minus 1/4 V of k equal to 0, where this nu is 3/2 plus epsilon. What is this? So this is a Bessel equation. Okay, this is a Bessel equation, and when you have a Bessel equation, you have a Bessel solution. Okay, so the solution is so V of k is equal to minus tau 1/2 C1 of k, where these are some constant that we need to fix as we did before, of minus k tau plus C2 of k h nu tau minus k tau. Okay, so this is the most general solution of a Bessel equation, where h nu is our Hankel function. And x, we can write x as minus k tau. So in the super horizon regime, h nu first, this is 1 and this is 2, of x, where x is this guy here, much bigger than 1, this as this approximate solution, 2 pi x e to the I x minus pi nu over 2 minus pi over 4. So h nu 2, again in the super horizon regime, as this form here, 2 pi x. It's pretty similar. There is a minus here, minus pi nu over 2 minus pi over 4. Okay? So so we need to impose the initial conditions. So if we impose that in the regime K much bigger than AH, the solution match the plane wave solution, because we are going from sub-horizon to super-horizon. The one that I wrote you before, okay, e to the minus k, e k tau. Then we find that C2 of k must be equal to 0, and C1 of k must be equal to pi over 2 e to the I half nu plus 1/2 over pi. Okay, so this gives us the two constant in the solution. So at the end of the day, the solution of my equation of motion will be v of k of tau equal to pi half. Okay. Half e to the I nu plus 1/2 minus tau for the Henkel function minus k tau. Okay. So we can still do an approximation writing the Henkel function on super horizon like x minus 1. This one, like using the gamma function, so over pi e to the minus pi half 2 over nu minus 3/2. Sorry, this is a gamma Euler gamma function of nu time. Okay. X to the minus nu. Okay. So sorry, this gamma is the Euler function. So and then the solution, the final solution becomes the following: v of k that is equal to 1 over 2 k e to the minus a k tau for minus k tau much bigger than 1, and the other solution is k e to the I nu minus 1/2 pi half 2 over nu minus 3/2 gamma nu. One over square root of 2k minus k tau to 1/2 minus nu. And this is for minus k tau much smaller than 1. Okay, these are the solution of my second order equation of motion. So if I remember that my Hij of x and tau is equal to the sum over p times d 3k over 2 pi cube over hk of tau e to the ik x k of p, so it's plus hk star of tau e to the minus a k x of a minus k dagger times aij p of k. So then I arrive and I remember that my v of p of k and tau is equal to my mass Planck square over 8 tau h lambda of k and tau. I arrive at the conclusion that my, sorry if I run a bit of this, the final solution of this, of my gravitational waves is h over m Planck over k to the 3/2 times k over ah minus epsilon f of epsilon. Okay, this is the solution, where this f of epsilon is defined as 2 epsilon 1 minus epsilon 1 plus epsilon gamma 3 half pi over gamma 3 half. Okay, so this is the solution of my equation of motion. Okay, from this equation here, I can compute the power spectrum. Okay, so give me just 1 minute. So I want to arrive at define the power spectrum that is defined as k to the cube over 2 pi square sum over p h k of p square. Okay, so and if I plug back the solution that I find before, I arrive at this form h over mass Planck square h over 2 pi square k over ah to the minus 2 epsilon. That is usually written as in this way, at squared over k over ah to the nt. This is the form of the spectrum in the slow-roll approximation, okay, where this nt is equal to minus 2 epsilon, okay, and this at is related to the amplitude of the power spectrum. So yes, sorry, I was a bit fast on this.
Thank you, Angelo, for this very nice introduction. There are any questions? So, if there are no questions, thank again, Angelo, and thanks everybody. I think I hope to see you all tomorrow at the same hour, okay?
Okay.
Thank you, Angelo.
Thanks.
Thank you.
Thank you so much, Angelo.
Bye. Bye. Thanks. Bye.
So see you all tomorrow. Bye.